Why does a fundamental law of galactic motion seemingly break when we scale it up to massive clusters? The researchers behind this paper argue it simply does not break at all, provided we account for the flow of cosmic time. We start with the Baryonic Tully-Fisher Relation, or BTFR, which tightly links a system's total mass to its spin. But when astronomers compare individual galaxies to massive clusters, they find that clusters follow a parallel line that is strangely offset by about 0.7 decs. To measure this relation, scientists sum up stars and gas to calculate total baryonic mass. While disk galaxies rotate neatly, broadly similar velocity proxies, like velocity dispersion, are used to characterize the chaotic movement of galaxies within a cluster. Here is the core discrepancy. Both scale groups exhibit a power law slope of roughly 4. However, clusters have significantly more mass than their velocities would predict, creating a puzzling gap in the data. To bridge this gap without inventing new dark matter properties, the authors propose a solution rooted in the evolution of the universe itself. They employ the Nexus Paradigm, a theoretical framework where spacetime is quantized. In this model, the slope of the relation remains constant, but the normalization, the intercept of that line, evolves as the universe ages and expands. The authors derive an analytic expression where mass depends exponentially on lookback time. Practically, this means that structures formed at different epochs are being measured against different cosmic baselines. Galaxies typically formed early, around redshift 2, whereas clusters are much younger, stabilizing around redshift 0.5. This represents a formation time lag of roughly 5.2 billion years. When you plug that 5 billion year difference into their model, it predicts a mass offset of 0.65 decs. This precisely matches the empirical gap observed between the Spark Galaxy dataset and modern cluster catalogs. This result suggests the two separate lines are actually one universal law seen at different times. It unifies physics across 5 orders of magnitude in mass, without needing to manually tune parameters for different scales. However, this unification is sensitive to how we define the exact formation time of a complex structure. It also depends heavily on how astronomers extrapolate gas mass at the faint outer edges of clusters. To learn more, head to emergentmind.com.